Wait, is your part last for the MATLAB? My part last. Just not yet. Alright, can we start?
Yeah, pretty sure. Still preparing stream. Yeah, I think we can go. Oh wait, it's already live.
Are we already live?
Yeah.
Okay, right, can we stop projecting?
Oh. Wait, did I even name this? I feel like I didn't name this.
What? Yeah? It's just simply cheese though.
Can you name it after the live stream?
Right, surely. This is like pedantics, who gives a fuck?
Okay.
Wait, how do I just plug this in and it goes in? Or I just plug this in?
This is MATLAB, yeah. And then MATLAB is like here.
The shit better turn on. If it doesn't, I'm gonna start swinging. Yeah. Yes. And then.
I don't think there's anything to do here, bro.
Wait, this is orchids.
Oh. What?
This iPad.
Where did you go?
The converter.
The whole thing.
Whole thing.
Oh wait,
I'll call her now.
I forgot. No, she knows.
She knows? Okay.
We good to go?
Yeah, should be good to go.
So it's recording?
I'll check on the YouTube.
Okay. So welcome to the MATLAB component. So we've just had the Maple component of this workshop. So all the engineers now know what to do for their software. But now we haven't forgotten the actuarial students. So if you wouldn't mind first scanning the attendance form, that would be quite nice. Right.
This is was editing the PDF. Do you remember? This is like wait, freeze it.
Oh, I don't know. It'll be alright.
No, I did it, guys.
Okay, whatever. Just one. Okie dokie. So we'll move on with the MATLAB part. You'll find that if you stayed for the Maple part, that a lot of MATLAB is analogous to Maple. Okay, and so a lot of the basics and the fundamentals run on a lot of the same stuff, right? So the way this workshop's going to be structured is. It's split up into 6 components. We've got the basics, and then MATLAB functions, basic calculus, collection of expressions, minimal amounts of plotting, and then linear algebra. Okay, that's what we have to look forward to today, right? So without further ado, I think we can just begin. We'll begin with the basics, okay? This is completely analogous to what was in Maple, right? So there are the basic operations, big 5, plus, minus, asterisk, backslash, and caret, right? So the way this looks is if I just do 1 plus 1, you get a cheeky 2 out the front, right? Similarly, if I do 2 times 4, cheeky 8, right? The same way, right, if I want to divide 4 divided by 2, right, you get 0.5, okay? All right, bye-bye. Right, so it should be pretty intuitive, right? Just using the same syntax that we like to use for the basic operations, right? But note that you can't put 2 operators next to each other. So if I want to do 1 minus minus 1, actually we can do 2 operators next to each other. Sorry, this is from the Maple, right? MATLAB is good because it uses a different sort of system for addition and arithmetic, right? And so if we want to do 1 minus minus 1, we're allowed to just say that that's equal to 2, which is good. Cool. Okay. We can also group more complicated expressions, right? So, for example, using parentheses, we can say -1 to a half, or -1 to the power of a half, or -1 to the power of a half in multiple different ways, right? So, seeing what this pans out, we end up getting -1 to the power of 1 divided by 2 gives me negative half, right? But if I were to do -1 to the power of a half like this, we get -1. Okay, so just want to be careful with how we use our brackets, right, for our order of operations. Right. Yep. Cool. And then we can also assign variables using just a regular equals, right? And exponential functions can be assigned using exp, right? With variable names, they have to start with a letter, and they are case sensitive. So if I did F1 and then I did capital F1, those are two different things, okay? And so as a sample output we have here, we let F1 equal 6, F2 equal expx, and we can let D equal some random number 1, 2, 3, okay? While we do have this, right, there is a difference between a double equal sign and a regular equal sign, right? For example, I could do 1 double equal sign 0, and that returns 0 with a blue text saying logical, okay? What this is meaning is that a double equal sign is a logical operation, right? It's comparing the two, okay? So in this case, 1 means true and 0 means false. So we've asked it a question, does 1 equal 0? And it's outputted 0, which is false, okay? Similarly, if I do does 1 equal 1, it'll output 1 because that's true, okay? That should make sense. If I want to clear my variables, I can just write clear, right? And if I want to get rid of all this clutter, I can just do CLC, like that, right? And then I'm ready to get started back again, right? And it's bad practice to name variables after special constants, like pi, right? And naming variables after function terms is also invalid syntax, right? Usually you'll find that it's a different color. If I write like an if, right, it turns it into a blue color because it understands that we're likely trying to write out a script rather than define a variable, okay? Pretty standard stuff, okay? And then we can unassign variables. That's what I did before, right? So if I just want to do A equals 1, B equals 2, C equals 3, and so on, right? Just keep mashing, right? You'll see on this bottom left part, right, I've stored a bunch of variable names, right? And so this is taking up memory space, right? And if I were to do like 2 times C, right, because I've already defined my C, it should give me an answer, right? But sometimes we do not want that, right? So if I want to clear everything, I can just write the word clear. And if you look on the left, it all clears, right? Should make sense, right? I can also ask just to clear specific variables by just naming the variable at the end, right? So if I wanted to clear just C, I would do clear C. But in this instance, C has already been cleared. And so, yeah, cool. And then constants, right? We got big 3, pi, I, and infinity. Can't live without them, right? And so they work how you would expect them to, so just get rid of all this clutter, right? If I did A equals pi, gives me 3.1416, which is pretty much pi, right? And then similarly, I can define something as I and infinity, right? And do the corresponding commands with that, right? And then we've also got displays, right? Displays of text and specific types of numbers using fprintf, right? So the way this works is I can use fprintf like this. Yep. And you can see it kind of guides you as to how to use it, right? But if I just do fprintf and I just do a bunch of stuff here, right? It'll just output the same text that I gave it, right? But this can be used more sophisticated, right? I could use instead fprintf, right? And I could say that in betwixt all my writing, right, I want to have a certain type of number, right? So in this instant, right, we have percentage .10f, right? I'll explain what that means in a bit, right? So percentage 0.10f, right? And then in order to do a line break, it's use the \n, right? And so what this refers to is it's storing a certain type of number, right? So f means float, so it's like a floating point number, right? And the 0.1 refers to the amount of decimals that I want this floating point number to be, right? And so if I just want, so I've put like a placeholder for the type of number I want to assign, right? So now if I just specify, oh, this number is 2, then hopefully, yeah. So it'll give me 2, but this time displayed as a floating point number, right? So 2.0000000 a bunch of times, right? If, for example, I had f print f with the exact same stuff, right? Dot dot. I'll do hyphens, right? And then, right? If instead I did, for example, point to e, right? This stores it as a different type of number, right? And so if I say this is 2, right? It does it in significant figure notation, right? It's just something to keep in mind, right? There are different ways. There's also integers for I, right? So for example, if I did the exact same stuff, command copy, command V, right? But instead I want to store this as I for integer, then it should output 2 as an integer, okay? It's just, we're putting different placeholders for the type of number we want, and then afterwards we're inputting the numbers, right? Should make sense. Okay. So now moving on to MATLAB functions, right? So we can express an anonymous function using kind of the @ symbol, right? And so the way it works is we can call the function whatever we want. In this example, it's f, right? And then we let it equal to @ of whatever our parameters are. So I'm just going to clear all this. So I could say f is some anonymous function, and I want this anonymous function to be in terms of x, right? So it's just saying f is a function of x, but then we have to actually define what this function of x is. So I could say, for example, it's just x squared, okay? So then it's defined what f is. So now, if I just plug in f of 1, it gives me 1. That's not too fruitful. So if I put f of 2, it gives me 4, okay? So the way this works is this @ is telling me it's a function of just x, and then immediately after, I say what the actual function is, right? So x squared, okay? And then that's exactly what they have here, right? So expression assigns a value to a variable using e to define an expression. An expression can be evaluated directly by assigning values, but a function takes in inputs and produces outputs, right? Expressions are just lines, functions are actual relationships, right? And the functions being called using input values, for example, f of 4. Cool. And so for an example like this, right, we want to do the distance function in 3 dimensions, right? So this is just going to be square root x squared plus y squared plus z squared, right? So what this looks like is d is our function, right? And it's a function of x, y, and z, right? So first we just define what our parameters are, and then once we do, once we know what the parameters are, right, we can define what the actual function gives us, which will just be x squared plus y squared plus z squared, right? Which gives me a function like that. And then now I can just start finding distances of whatever I want, right? So I can say d of 2, 2, 2, and it gives me whatever the number is there, okay? Should make sense, right? It's always just a case of d is a function of whatever it's a function of, and then you have to specify what it's actually doing, okay? And then we also have a bunch of built-in functions, right? So we can specify our own functions when it gets a little more complicated. Otherwise, the basics, we already have words for those. And I've already used this in one of the previous slides, right? You saw me use sqrt, which is usually common notation for square root. But otherwise, I can use abs for an absolute value. I can use sqrt for a square root, sine for sine, a sine for arc sine, and so on, right? And so, clearing all this garbage, right? If I want to do sine of 0, 0. Isn't that fun, right? Cos of 0, you're never going to believe it. 1, right? Because cos and sine are inbuilt functions, right? We also have the exponents that we talked about, which was exp, right? So exp, this would just be e squared, which is around 7.4, right? We also have our absolute values, right? So the absolute value of 2 minus 5 gives me 3, right? This should make sense, right? Then we also have square roots, which I used before. Arc sine, arc cos, we just append an a to the front, right? Otherwise, it's more of the same, okay? So now we move on to piecewise functions. These are a little more complicated, right? So we said before that if we want to define a function, first of all, I'll clear all the functions I've already made using clear. And then I'll do CLC to get rid of all the clutter, right? So if I want to define a function usually, right, I say f is a function of, f is at of x, right? So it's kind of getting MATLAB ready to start making some functions, right? But sometimes we want to do it piecewise, right? And the way we do this is we put the condition on x, right, in brackets. So like x less than 0, or this, and then we append a dot asterisk before showing what the function value is, okay? It's a bit technical to explain, but it should make intuitive sense just by looking at it. What it's saying is when x is less than 0, this function is equal to 0. When x satisfies these conditions, this function is equal to x squared, you know, and so on, right? And we join these with a plus, okay? So what this would look like, because I'm not going to write out this entire essay. Okay, is that when x is less than 0, we have 0, plus when x is between 0 and 1, we have x squared, plus when x is greater than 1, we have 2x minus 9, okay? And then we can say, okay, well, if x is less than 0, so if I have negative 2, it should give me 0, and it does, right? X is between 0 and 1, so say 0.5, should give me its square, 0.25, right? And then if x is anything greater, like 100 or just 10, gives me 19, okay? One thing to note here is that you'll see that these values of x have a little full stop next to them. Okay, this is an important distinction. Okay, so the way that MATLAB stores things is it uses what are called arrays. Okay, so these could be your row vectors, your column vectors, your so forth, right? So for example, if I wanted to do a function of x, right, where it's just x squared, right? We can do this, right? And we just use our regular, f of 2 equals 4, right? But what if I wanted to apply this to a vector, right? We'll get onto vectors in a bit, right? But right now, if I try and apply this to a vector, like 1, 1, it freaks out, right? It doesn't know what to do because we only define this for x, which is a real number, right? And so what in the previous example, we had the same thing, except before the exponentiation sign, we had a full stop. And what this tells MATLAB to do is whenever you see a vector, right, you apply the function to every element, okay? So what this looks like is if I just call this one g, right, this now inputs, this allows inputs of scalars and vectors, right? So yet again, if I do g of 2, it'll give me 4, right, which is good. But now if I have g of a vector, right, for example 2, 3, it gives me 4, 9, okay? So it's just something to keep in mind that if we want to incorporate vectors, right, and linear algebra into our functions, we have to worry about this full stop before all of our operations. Clear NCLC. Okay, and so that's what we have here when we have x dot squared. Okay, and then finally we have functions for simplifying, right? So MATLAB provides functions for simplifying expressions using symbolic math, right? The factor and expand commands can be used to factor and expand, right? Simplify can be used to simplify, right? And we can combine or simplify can help with rational expressions, right? This shouldn't seem too crazy, right? So here, right, we have, for example, if we want to factor this, right, or expand this, right, we can just use that, use the corresponding, unrecognized variable x, right, that's right. This has to do with the fact that I didn't clear, right? But we can just use factor, expand, simplify, and combine, and so on, right? To get different factorizations, right? And you usually have to specify what you're factoring with respect to and simplifying with respect to, as is with Maple, right? And so you have sims xab, factor, expand, simplify, and combine, right? I'll leave it to you guys to try these because these will take a long time if I do these myself, right? Otherwise, we can keep going onto basic calculus. So is that you?
Alright, so we'll move on to basic calculus now. So to begin with, we can use the limit function in MATLAB to evaluate limits. So this requires the symbolic math toolbox or extension, which is already embedded into the software. And we can also use right or left to evaluate one-sided limits. So what we're going to do is, on MATLAB, I'll just clear everything. Alright, to start off with, I'm just going to do sims x. So this just declares it as a variable. I'm going to first declare my function f, and I'm going to make this sine x on x. So once I have this over here, what I can do is I can use the limit function to find what the limit is as the x value approaches a specific number. So for example, let's say I want to set L to limit brackets f x 0. Once I click enter, I should get L is equal to 1. And yeah, so that basically works where even if you put right or left into the function as well, and for any x value, whether that's 0 or any valid or within any valid range. Moving on, we can also do derivatives on MATLAB. So we will need to use the derivative and substitute functions to work with both indefinite and definite integrals later as well. So how this works is, I'm just going to clear everything out again. So I have my x and y variables. What I'm going to do is I'm going to define them in this function. Let's say I have x cubed plus 4y squared. Once I click enter, what I can do is I can differentiate the function f with respect to both x and y. So I'll first differentiate with respect to x. When I get this, I should get 3x squared. Clicking enter, that's what I get. Similarly, if I differentiate with respect to y, I should get 8y. I can also differentiate several times. So if I wanted to find the second derivative with respect to x, for example, if I do diff f x and then 2, what this does is it differentiates the derivative again. So now I should get 6x, which is what I have over here. And I can also differentiate using different variables one at a time. So if I do f comma x comma y, what this does is it differentiates f with respect to x, so it gets the function to 3x squared, and then it will differentiate with respect to y. And because there's no y in the expression, the answer will just be 0. I can also substitute different numbers into the derivative. So for example, if I do subs, then brackets, I have to do diff bracket the function with respect to x. Then I want to replace the x variable with the number 2. So what this does is it will replace x with 2 into the first derivative with respect to x. So that was 3x squared. Once I click enter, I get the number 12. Because if I put in 2 into x, 2 squared is 4, 4 times 3 gives me 12. I can also solve differential equations. So if I use the solve function, then type diff, and then I do the function with respect to x, and I let this equal to 0, where I want to solve for x. When I click enter, I should get 0 for my x value. So if this is equivalent to solving 3x squared is equal to 0, where x would be 0. Moving on, we also have further derivatives as well, where we can use the substitution and solve function to evaluate and check for critical points. So we've already covered this a bit, but I'll still go through some parts. So let's say I want to make a new function. Let's do the function f is equal to x cubed minus 3x plus 2. So we have our function here. What I can do is I can use the substitution function. Alright, so before I do that, so earlier we were doing diff f of x. What I can do is I can also declare it to another variable and then you plot that or substitute that variable into the substitute equation. So let's say I have df is equal to diff f with respect to x. So what this should give me is 3x squared minus 3, which is the derivative of this function over here. So now, in the substitute function, instead of having to type diff f and x, I can just type in df, which is what I matched it to, then x and 2. So this should replace x or sub 2 into x into the derivative, which gives us 9. I can also do critical points. So let's just say I can name my variable anything, crit points, and I want to solve the derivative, the first derivative with respect to x being equal to 0, and I'm solving for x. This gives us the two solutions which are valid for allowing 3x squared minus 3 equal to 0. Moving on, we can also do integration. So this includes both indefinite and definite integration. So moving back, I'm just going to clear my screen again. So let's say I have the variable x and my function is 6 times x to the power of 8. So if I was working with my indefinite integral, I can label this as anything. If we do the integral function and then we do f comma x, what this does is that it'll give us the function which is the integral of our original f. I can also do definite functions or definite integrals, where if I do the integral f comma x, now what I need to do is I need to label my bounds. So if I want to integrate between 0 and 1, I type 0 and 1. And what this will do is it will substitute the bounds into this indefinite integral here to give us the numerical value of 2 over 3. So it doesn't matter what we're labeling the functions as. So indef and def could also be like a is equal to integral of f of x, f with respect to x, and let's say we're taking the derivative twice, that's my integral over there. Alright. So now moving on to collections of expressions. So we'll be going through sequences, lists, and briefly on matrices, which will be covered by Unu later as well. So a sequence can be defined in two main ways. So we can have an explicit range, or we can do linear spacing where we have a start and end point and we specify how many different numbers we want in between. So let's say, for example, I have years, and I want to label all the years from 2026 to 2050. What the 2 in between does is that it spaces the interval out by 2 for each year. So it will list all the years from 2026 to 2050, skipping 1 year. If I were to do the exact same thing where I do 2026, 1, 2050, this will label every single year, inclusive of 2026 and 2050. So if the interval is just 1, you don't necessarily need to include it in the middle of the two numbers. But yeah, this is very helpful if you know how far apart you want your numbers to be. So if I wanted to do 0 and intervals are 0.25 to 1, it'll give me 5 numbers for 4 equally spaced intervals. I can also do the sequence function or linspace, where I label what my start and end points are, and then I also specify how many distinct points I want in my output. So when I do 100, what this does is that this 100 is inclusive of the 0 and the 1 at the end as well. So it won't necessarily be spaced out 0.01 by that interval. If you wanted to do that, that would have to be linspace 0, 1, 102. Sorry, linspace 0, 1, 101. Yep. So if I wanted to space the intervals equally by 0.01, between 0 and 1, I have to use 101, not a 100, because we're also including the starting and ending number as well, which is why the earlier method, which was just listing how many, listing the start and end, and then listing what the interval you wanted it to be, is also easier. So if I wanted to do that here, I can just do it like this. So in this, I don't actually need to specify how many like distinct numbers I want. It'll just do it itself. So it'll just make sure that every number is spaced out by 0.01. Alright, so now moving on to lists. So these contain elements of the same type. So if you need a list that contains mixed data like a string, matrix, or scalar, you can use a cell array. And the syntax is the curly brackets. So in the list, we don't necessarily need to have numbers. We can also have vectors or words or phrases as well. So let's just say I have my list here. I can label it as anything I want. With my curly brackets, I'm just going to type anything. So MathSoc 2026, and let's say I have a vector. Okay, just noting, when you're writing words, you need to have the apostrophes around. I'll do that again. So I'm going to have the apostrophe symbol, MathSoc 2026, and then my vector. So what this will produce is a 1x3 cell array with all three outputs. So now let's say I want to pick a specific item where I want to select the second element. What I have to do is I have to type my variable name, which is list, then 2, and this should give me the second element, which is the year 2026. Moving on to sets. So MATLAB treats any vector or cell array as a set when you use built-in set functions. So we'll skip this. You can use these functions to find like the union or intersection between different variables. Now moving on to matrices, which will also be covered by UNO as well more extensively. So this is just a brief overview over here. So if I have, let's say, I have my matrix A, which is 3, 2, 1, 2. So what this does over here is it creates a 2x2 matrix, where in my first row I have 3, 2, and in my second row I have 1, 2. I can also create a vector where I have this, and what this does is it creates a column vector with 18 and 10. If I wanted to do a row vector, so let's say I had 5, 6, I would have to separate the two numbers with a comma instead of the semicolon, and there we have that over here. If you want to solve linear equations in this form over here, where ax is equal to b, and you want to solve for x, what you can do is you can use the backwards slash. So if you do a backwards slash b, it will give you the actual answer. So I can do this, a backwards slash b, and that's my output over there, the column vector 4, 3. So if I go back, what that means is that the matrix A with the column vector x will produce the vector b. So I can test that out as well. And there we have our 1810 column vector. We can also use matrix operations as well. So these are the more common matrix operations which are used in 1151. So to begin with, let's say I have my matrix A. If I want to find the transpose, I can just type the matrix name and then with the apostrophe next to it. What the transpose is it just swaps the rows and columns around. So earlier my first row was 3, 2, and then second row was 1, 2. But now my first column is 3, 2, and my second column is 1, 2. So it just swaps everything around. I can also find the determinant of A, where I can just do det and then in brackets write my matrix name, and this will give me the answer 4. So what the determinant is specifically within a 2x2 matrix, it's just this value over here times this value, so 3 times 2 minus 2 times 1, which is 6 minus 2 giving us 4. I can also find the rank which gives us 2. The row reduced echelon form of, let's say I had I'll do matrix A first. So the row reduced echelon form of matrix A is just the 2 by 2 identity matrix. If I wanted to augment the matrix, so let's say I had this over here. So what augmenting does is that by including these two matrices in the square brackets, it just smashes them together. So this first part over here is matrix A, and this was our column B, and now it's become a new matrix, which was answer, or I can do C is equal to answer. So now the variable C is our new matrix. So if I wanted to do the row reduced echelon form of this, I can also do this. And there we have our output. I can also find the inverse of matrix A, which is this over here. Keeping in mind that a matrix won't have an inverse if its determinant is 0. So yeah, I already showed the augmentation of the different matrices. And yeah, that concludes this slide. And now we'll move on to plotting, followed by linear algebra, taken over by Uni.
All right. So plotting a single variable function, we're going to be using the fplot function. So what you can do is I'm going to clear. So the way you plot things is you just do fplot, like what Ahmed said. You have your @x, and then you want to write the function that you want to plot. So for example, if I want to plot sine x, I can do sine x, and then you would write your interval. So if I want to plot sine x from -2 pi to 2 pi, I would write -2 pi, 2 pi, close all my brackets, and that should give me a plot. There we go, there's sine x from -2 pi to 2 pi. Now suppose I want to restrict the range as well. We're going to be using the y-lim. So here, let's use the same function I used, but this time I can write y-lim. Let's say I want to restrict sine x from -0.5 to 0.5. So that's -0.5, 0.5. And there we go, there's sine x. But it's not limited to just the range. For example, I can also limit the range from, let's say, -2 to 2. And that gives me sine x from -2 to 2 as well. If I want to plot multiple functions on the same axis, then we're going to be using hold on, hold off. So if I want to, let's say I'm going to plot sine x again from, let's say, 0 to 2 pi this time. So what I'm going to say is I'm going to say hold on, and then I'm going to plot my second function. So let's plot tan x from 0 to 2 pi. And then after it's hold on, I'm going to tell it to hold off. And there we go. That plots sine x and tan x on the same graph. So essentially, after you plot the first function, you're going to tell it to hold on, plot the second one, then hold off. Now to plot parametric plots, we're going to use linspace like we used before. So first, I'm going to define my parameter t as linspace from 0 to 2 pi, and let's have 100. And now I'll plot x equals cos t, y equals sine t, and then using my plot function, so plot xy, this gives me my parametric plot, which is a very squished circle, but yes. How about if you don't want to use linspace, you can also use fplot again. So fplot, but this time we're going to do the @t twice. So @t cos t, and then @t sine t. And let's do it from 0 to 2 pi again. And that should give our same circle as before. So polar plots and implicit plots. So MATLAB, we don't have to do any of the maple with plots, any of those stuff. It has built-in plotting functions. So polar plot, we're going to use polar plot theta comma r. So we have to first define theta as linspace. Let's go from 0 to 2 pi 100 again. And then I'm going to define r as 1 minus cos theta. So r is equal to 1 minus cos theta. And then after you defined your theta and r, what you can do is you can now write polar plot theta r. And pressing enter, this gives me my polar plot. Okay, just disappeared. But if you don't, oh, okay. And then now for implicit plots, we're going to use the f implicit function, right? And like how before we used at x and at t to define functions in terms of x and t. If I want to define an implicit function, it's going to be at x, y. If I want to define an implicit function, that's in terms of both x and y. So as an example, I'll have x dot y, so x times y, minus 1. And the way you would set it out is you would have brackets, and then you have your domain. So for example, you can have your domain from minus 5 to 5. And then in the same brackets, you would write your range. So for example, minus 3 to 3. All right, so this function is an implicit plot of xy minus 1, which is not loading.
Wait, can you explain where you like wrote all the numbers in a row again? Like for the implicit?
Yep.
Like the
Which line?
-5, 5, -3, 3.
Yeah, so that line is just me setting my domain and range.
Oh, okay.
So the first two numbers are my domain, -5 to 5. And then in the same brackets, you write your next two numbers. So my y's go from -3 to 3. Where'd the actual plot go? Is it hiding behind the tab?
Yeah, maybe. Just like don't risk it. Don't risk it.
All right, you can. It's gonna pop up.
You can clear it out.
Yeah.
Oh, clear. And then I'll just try pasting it again.
Do CLC.
Yeah, I think it might just be like behind.
I think it might be behind the screen, yeah. But like before, a plot would show up. Hang on, everything's plotting. Where did it go?
It's fine. Like,
Maybe we can move the tab around. Oh,
there
it might be that.
Yeah. Okay,
Yep.
it's just behind.
Yep, we found it. How do I move it in front?
Oh, no.
What is happening? Okay, there we go.
It's fine. You don't need to worry about this.
Okay, now I'm just gonna keep it like that. Plotting. Now we're gonna plot data points, right? And to plot data points, you can either plot them separately. So here, x is equal to square brackets 3, 15, 9, 6, and so forth, and y corresponding y values. And the way it works is, let's just plot something simple. So 1, 2, 3, and y is equal to 2, 3, 4. You would do plot x, y, and then you would choose what kind of marker you'd want to plot. So for example, if I want to plot it with O's, I'll do apostrophe O. And what that does is it gives me the points 1, 2, 2, 3, and 3, 4 with the circles O's. However, I can also plot x, y with dots instead. If I don't want to use circles, I can use dots. You can't really see the dots, but they're there. Right. We can also let x equal 0.1 times 1 to 100. And what that means is, so the 1 to 100 is, we let x equal 1, 2, 3, 4, all the way to 100 and so forth. And the 0.1 just multiplies it all by 0.1. So what I'm basically doing is I'm making x all the values 0 0.1, 0 0.2, 0 0.3, all the way to 10. And then using that, I can define y to be sine x. So that means it's going to plot y equals sine 0 0.1, sine 0 0.2, sine 0 0.3, and so forth. And then plot x, y. Let's use O's this time. There we go. There's sine x in O's, or circles. Now on to very basic linear algebra. Vectors you define with square brackets. Right? If you want to make a row vector, you either use commas or spaces. So here, if I want to say clear, this first clear. U is equal to 1, 1, 2, 3. It makes a row vector. If I want to make a column vector, I'm going to use semicolons. So V is equal to 1 semicolon, 2 semicolon, 3 semicolon. There's a row vector and a column vector. Right, like how we can add and subtract vectors, we can also do that on MATLAB. So here, if I want to add, or I guess multiply, u by 2, I'll do 2 times u, and that will give me 2, 4, 6. If I now define another vector, let's say 3, 4, 5, I can do u plus w, and that gives me 4, 6, 8. So you can add and subtract vectors like how you can imagine they would add and subtract. Right, matrices, you can imagine I'm doing 1, 2, 3, which is the first row, and then a semicolon moves it to the next row. So 1, 2, 3, next row, 4, 5, 6, next row, 7, 8, 9. So I can make a matrix B. Let's have 1, 2, 3, 4, 5. That's my first row. A semicolon then moves me to my next row. 1, 2, 3, 4, 5. And there's my matrix B. All right, similar to vectors, you can add and subtract, multiply matrices by scalars. So let's let C equal 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. And then we can do B minus C. And that gives me my matrix. Pretty straightforward. You can also multiply 2 matrices together. Same thing again. Just add an asterisk between 2 matrices and they'll multiply. If you want to extract specific rows and specific columns, you would write your matrix. So for example, in my matrix, let's make a new matrix. Let's make A, 1, 2, 3, 4. If I want to extract specifically the first row, I would write A bracket 1, comma, colon. So here it will be A, 1, comma, colon, which is my first row. If I want to extract my first column, I would write A, colon, comma, 1 instead. And that gives me my first column, which is 1, 3. So if I want to extract my row first, my number will come before the colon. And if I want to extract my column, the colon will go before the number. And you can also perform vector addition and subtraction using the extracted rows as well. MATLAB also has built-in functions for special matrices. So, for example, the identity matrix is given by I. So if I do I, 3, that gives me my identity matrix, or 3 by 3 identity matrix. I can also do I, 5, which is same thing, but now it's a 5 by 5 matrix. I can also do the function diag for diagonal. And what that does is if I put in 1, 2, 3, it gives me a diagonal matrix where its diagonal entries are 1, 2, and 3, and so forth. So that means I can put in 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6, and it creates me a matrix where all its diagonal entries are 1, 2, 3, 4, 5, 6. I can also use the functions ones to give me a matrix that has entries all 1. So here, if I do 1s, 5, 4, that will give me a 5 by 4 matrix where its entries are all 1. But what if you want a matrix where you want its entries to be all 2 or all 3? Well, you can do 2 times 1's 5 by 4. And there's your matrix with all 2's. Finally, if you want the zero matrix for some reason, you can just do the same thing, zeros instead of ones. Yep, and so that is I, which is the identity matrix. Diag for the diagonal entries, ones and zeros. Pretty straightforward. You can also do operations with these as well, so diag plus diag. The command rref will give the reduced row echelon form. So A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. REF A. There's your reduced row echelon form. Right. And solving linear systems, we already covered this already. You have your matrix, you have your B, and then backslash would solve AX equals B. Right, and that is the end of the MATLAB workshop. Right, thank you guys for coming.
Thank you for watching.
Yeah, thank you for watching online. Bye-bye.
Okie dokie.
Appreciate it.
No worries.
How do I close this? 22 views. That's bad.
Wait,
How
is
do
this
I-
live?
Yeah,
Yeah.
I
in
thought we
stream.
were like pre-recording and then.
Oh.
Nah.